All right, we are in Unit 3. This is the second video, and we're going to start by talking about electron orbitals. Think of a typical drawing of an atom. It might look something like a model of the solar system. So you've got this big nucleus piece here, you've got a circular orbit with something going around, another circular orbit with something going around. This might be your thought, or more than likely the more artistic version of this one. So we've got this nucleus, we have an orbit like this, an orbit like this, and another orbit like this. This is probably what you're thinking of when you think about atoms. So this one is the Bohr model of the atom. It's an older model of the atom, but it works well on paper, mostly because it's easy to draw. Each orbit is an energy level. So an orbit that is farther away from the nucleus has a higher energy than one that is closer. I compare the energy levels to the rungs of a ladder. So electrons have to stay within the energy level. An electron cannot exist between energy states, just like you can't stand in the space between ladder rungs. As you climb the ladder, your feet have to be resting on a rung. If you try to stand in the space above it, you're going to fall down. Best case scenario, your feet will hit the next rung. Worst case scenario, you end up on the ground. The reality is that electrons do not orbit in neat circular orbits. Instead, we have this idea of an orbital. Note the difference in the terms here. Orbits versus an orbital. An orbital is an area where an electron is likely to be found. An electron will spend 90% of its time in that orbital area. Any individual orbital can contain a maximum of 2 electrons, pairs. In the current model of the atom, each energy level is divided into sublevels. So we have an energy level, then we have sublevels, and each sublevel can be divided into 1 to 7 orbitals. So we're going to look at sublevels and orbitals in some detail, and then we'll summarize it at the end of the video. There's really 4 types of sublevels. The first one is called S. They are just given letters, and they are not consecutive letters. They're not alphabetical. They're just letters. S sublevel has a spherical shape. It contains 1 orbital. Look up here. Any individual orbital can contain a maximum of 2 electrons. So this one has 1 orbital, meaning that this S sublevel can hold up to 2 electrons. The S sublevel fills first in every energy level. And if you're looking at the periodic table, it correlates with groups 1 and 2 plus the element helium. The periodic table is arranged a very specific way, and it has a lot to do with energy levels, orbitals, and electrons. The next is the P sublevel, and this one has a dumbbell shape. And by dumbbell, I don't mean that it has this nice shape like this. We just call it a dumbbell. It actually has a shape that is more like if this is where the nucleus is, something like this. It really looks like two balloons that are tied together in the middle, and they call it a dumbbell shape. The p sublevel has 3 orbitals. Looking back at this rule up here, an individual orbital can contain up to 2 electrons. This means that the p sublevel can hold up to 6 electrons, up to 6. The p sublevel first appears in the second energy level, and it fills after the s. Remember, the s fills first in every energy level. The p fills after the s. On the periodic table, this group typically corresponds with groups 13 through 18. The d sublevel contains 5 orbitals, and they have weird shapes. We're not going to concentrate too much on the shape in this class yet. At the very end of the year, when we talk about molecular geometry, the shape of a molecule, this will come back into play. But for now, just a brief description. 4 clover shaped. So we're talking about, here's a clover shape, 4 of these, and then 1 that's a donut shape. Keep in mind that this is the theory. We've never actually seen what these orbitals look like, but we have a good idea based on some different observations. 4 clover shaped and 1 donut shaped. This sublevel can hold up to, remember, each orbital holds 2 electrons, meaning that the d can hold 10. The d sublevel first shows up in the 3rd energy level, and it corresponds to groups 3 through 12 on the periodic table. These are the transition metals. As far as chemistry 1 is concerned, the d sublevel is about as far as we ever work. There is another one. It is called the f sublevel, and this one contains 7 orbitals. Most of these have a very complex shape, and each one of them resembles 6 or 8 balloons tied together. It's an odd shape. The f sublevel can hold up to 7 orbitals with 2 electrons each. That's 14 electrons. It first shows up in the 4th energy level, and this one corresponds to the inner transition metals. So there are some patterns here. I always like to look for patterns, and there are a lot of patterns in chemistry. So looking at these sublevels, first sublevel has 1 orbital. Next sublevel has 3. Next sublevel has 5. Next sublevel has 7. 1, 3, 5, 7. As far as what they correspond with on the periodic table, so you're basically going from left to right and then top to bottom, almost like we're reading. So S sublevel is groups 1 and 2 plus helium. Those are the 2 on the left side, and helium's off by itself at the top right. The P sublevel, 3 orbitals, 6 electrons, corresponds to groups 13 through 18. This is 6 different groups on the periodic table. The D sublevel, 5 orbitals, 10 electrons. Look at the transition metals. There are 10 vertical columns corresponding to 10 possible electron configurations there. The F sublevel can hold up to 14 electrons. If you look at the bottom of your periodic table, they're not numbered, but you can count them. There are 14 columns of elements in the intertransition metals. So you can see how these are starting to relate to the shape of the periodic table.